right, let me say a couple of words about the second class homework. The first one is an application of the Chinese Remainder Theorem. We did one similarly in class. This was a little bit more sophisticated. Consider the ring Z mod 43,200. Count for me the units, the zero divisors, and the drill codes in this ring. So it's kind of a counting problem. Make sure that it's clear how you're getting your number, right? I mean, this doesn't really require proof, but just make clear where everything's coming from. Number two, we're going to talk formally about polynomials and formal power series in the next section after this next one. But this is kind of warm up. We've done stuff with polynomials already as sort of examples, and here we make some things formal. The ring of polynomials is just a set of all polynomials and coefficients in some ring. If you add two such things, you get another polynomial and multiply. The multiplication is the way you're used to. Add it, it's just degree wise. Multiplication is given this way, where the term is this, and this is your regular polynomial multiplication that you're used to. If f of x is a polynomial and the leading coefficient is not zero, we say the degree of f of x is n. Show that if R is an integral domain, then the degree of f of x times g of x is the degree of f of x plus the degree of g of x. This is not true in general if R is not a integral domain. Show R is an integral domain if and only if the polynomial ring is an integral domain. So integral domain is preserved in polynomial extensions. Show if R is an integral domain, then the units of R are exactly the units of the polynomial ring. So the things that are invertible in the polynomial ring are precisely the things that are invertible in the ring itself. Show that if I is an ideal, then this construction here, ix, which is just a set of all polynomials, all of whose coefficients are in the ideal I, show this is an ideal of Rx. Show that Rx mod Ix is isomorphic to R mod Ix, so this is a polynomial in itself. And conclude that I is a prime ideal if and only if Ix is prime. Here, what I mean, I should have said this more clearly. I is a prime ideal of R if and only if Ix is the prime ideal of Rx. Yes.
For B, if I have C as my ring and then C adjoin X as the polynomial ring, but then if I mod out by the relation, is that if that X squared equals 0, is that a different ring? So
yeah, that's different. That's not a polynomial ring. And finally, show the ideal Ix in Rx. So this is the smallest ideal in Rx that contains all the elements of I in the element X. Show that this is maximal if the ideal I in R is maximal. Don't try to prove the other direction of this because it's not true. You might see if you can find the counterattack. And finally, just kind of as a teaser, we're going to, like I said, we're going to talk about formal power series as well. You can go back and replace all the polynomials with power series right here. And my question here, a challenge problem to think about, is which of the following, or which of the results that we had follow an analogous form, which have to be tweaked a little bit or just flat aren't true, and are there results that are better for polynomials, whatever that means, power series. So the point of that is just think about how analogies would work for power series, if at all. Okay. Questions? All right. Okay. So we were in the throes of proving this stuff about the Chinese Remainder Theorem. R is commutative ring of identity. These are ideals. We verified that this function here is a homomorphism, and now we're on to doing this part. Continue.
Yeah, I've already kind of been up there like on my own time, because I was born one time. From Wednesday, expecting to prove that though.
So, what we'll do now is we're gonna look at K equals 2, just to make this, a little bit, easier. So the case K equals 1, the fact that this holds K equals 1 is just straightforward by definition. K equals 2, we'll do this just for convenience of notation. Now, I claim that so we're assuming the statement down here that the ideals are pairwise comaximal, y plus J is R. And yes, F from R mod I J, R mod I. Actually, no, I'm gonna do this. And I'm gonna find this way. Now, we know that this is a homomorphism. F is a ring. I claim it's on. So here's the strange part. So suppose right, and this is not so clear because f of x is x plus I comma x plus j. How am I going to get it to be these two things? So, any ideas on how we might do this? So and let's say, I guess. Our assumption is these ideals are comaximal, so I plus j is R, and we also have certainly A minus B. Here, relevant A and B. A minus B is an element of R, right? So there exists alpha in I and beta in J, such that because any element of R can be written as something in I plus something in J, so I can do that. Right?
Yep.
So
That's why we kind of did in the proof.
this is, let me rewrite this cosmetically. I'm gonna write this as B plus beta, right, and this is, right, A minus alpha. So I'm gonna call this element X. This is an element X that I can write two ways. I can write it as B plus beta and A minus alpha. Agree? Now consider this is replacing X with A minus alpha. and replacing x here for b plus beta. And notice alpha is in I. So this is the same concept as A plus I. And beta is J, so this is B plus. So X two. Okay. So F R mod I mod J given by F of X equal X plus I X plus J is on to. And kernel of that is equal to I intersect J.
And it's a,
We proved that last time in a more general sense, that the kernel of this map is I intersect J. And we have an equality here as I plus J R.
then use the first isomorphism theorem to prove the case.
Right. We proved this equality last time. And so, since this is on to and the kernel is IJ, this implies by first isomorphism theorem that R mod IJ going to work R mod I cross R mod. Everybody okay? That is the case for two ideas. Inductively, and I'm not going to go through the details of this too much because it's almost exactly the same. We have already done, like I said, the heavy lift. Assume statement holds. For K is M, and now suppose I want I n plus one or pairwise combines. So we're going to assume that this statement down here holds when you have n pairwise comax modules. Now assume that we've got n plus one.
Yep.
So now I'm just going to go back to the two cases. Let I be I1 and J be the rest of them.
You can basically make one of those things to another ideal.
Well, what do I need to do?
So if we can compress two of these things to make it to an ideal, because an ideal finds another ideal.
We know that these are an ideal. We've already proved this. We need their comax.
They are comaximal because I2 and comaximal with I3 and I2 is comaximal with those things, so they just simply comaximal to the product as well.
I think we need to be a little bit more careful.
Okay, probably need to do it.
I claim that I and J are comax. If not, then I, J are both contained in some maximal ideal. Yeah. So I, J, and then some maximal ideal. Right. And what do I know about any maximal ideal? What other descriptor does it have? Any maximal ideal is also prime. And, you know. You remember our first definition of prime ideals? If an ideal is prime is when it contains a product of ideals, it must contain one of the ideals in there, right? L. Because in this prime must contain one of these ideals in the product. Therefore, M contains I1 and IL, which is a conflict. Because the ideals I1 of I2 plus 1 are supposed to be pairwise comaximal. So you can't have two of them individually sitting.
So they're co-prime,
Comaximal.
comaximal, I mean, comaximal.
Right. So it
Yeah, that-
contains both of these. Everybody okay with that?
Yeah, once again, else. Seems to be a recurring flaw, I'll need to work on it.
So now what we know is, and I'll do this briefly. We know that because we know I interior comaximal. And we did this, that was a step K equals 2 that we went through all the trouble with earlier. And this is isomorphic. R mod I1 cross R mod I2, I3, plus 1. But these are all pairwise comaximal as well. And now there's only M ideals here, and so the inductive hypothesis applies. And this is isomorphic R1 cross R mod I2, R mod I3, R mod I4. So there's our inductive hypothesis. We've got the next step. Any questions on that? Okay. What we're going to do now, I'm going to go through this pretty quickly because you've done some of the stuff yourself in the homework. We discussed multiplicative sets, but I'm going to have some more gems in here for you. Oh, this is I'll call this multiplicative sets and localizations. Definition 941. I'm going to assume in this section pretty much that R is a key to bring identity, although you can certainly find multiplicative sets in a more wider universe. S and R, I'll assume it's not empty, is a multiplicative closed set. If S, T, S implies S. So I think that this is reflective of what you would think it is. It's just multiplicative closed. Give me two elements and set this products in.
Yep.
And we would usually assume by default that 0 is not an S. And we'll see why that's.
Well,
Right,
anything else, I need to go over my homework again, just, do an proof check, because apparently meeting records.
So, what's one ring that you think of is the rational numbers, right? And the rational numbers are made of fractions, right?
Yeah, they're close.
Integer over integer, right? So let me do kind of a motivation. Okay, since y'all are my sciences majors, please tell me that you can answer this question.
Okay, so say. Sin of 21.
Right, and what's the convention here, right? You have to have a new denominator, and what's the new denominator that you have?
These come in multiple, 21.
This is the way you're used to adding fractions. More generally. If I agree with that. One of the reasons we're talking about multiplicative sets, we're building to something. How to talk about fractions. When you're used to adding fractions back in the old days, if you had denominator B and denominator D, basically what you need to add those fractions is you need B times D to also be a denominator, right? That's what you need to make the game work, both for the addition of these fractions and to multiply the fractions, right? So this is kind of a look ahead to where we're going. But one of the important things about multiplicative with both sets is it allows you to make fractions, right? Where your numerators come from a ring, anything you want, in the ring, for example, and your denominators come from some multiplicatively closed set, which you certainly don't want a denominator to be zero, probably. We'll see what that's true, right? So for example, if you think of the rational numbers, it is any integer you want in the top. And what kind of integer do you want in the bottom?
Non-zero.
As long as it's not zero, right? Look at the non-zero integers. Non-zero integers. That is a multiplicatively closed set. Because when you multiply two non-zero integers, you get non-zero.
Yep.
You can have more exotic sets. For example, you can look at all fractions that have an odd denominator, right? This is a ring that contains the integers, right? Because any integer has an odd denominator, integer over 1. Right? This is a ring that contains the integers, but is not quite all the rational numbers, because, for example, 1/2 is not there.
Yeah.
But any odd denominator, what happens if you add two fractions that have odd denominators? You get a new fraction with an odd denominator, right? And multiply the same. So that's kind of a look forward as to sort of what the justification or motivation for this is.
I was trying to get really interested.
So, if R is equal to ring, then R minus 0 is a multiplicative set. Because in an integral domain, A times B equals 0 means either A or B is 0. So if you multiply two non-zero things, you got to get something that's not zero. You do need domain. The units bar is a multiplicative set. Because if you multiply a unit times a unit, you get a unit. Another example is the odd integers is a multiplicative set. So there's just a couple examples. Definition. A multiplicatively closed, and I'll tell you what I mean by putting that in parentheses. Set A in R is said to be saturated if it contains all the survivors. Let me be more precise about being here. If X times Y is in this set, then X and Y are in this set. So it's kind of a dual notion, multiplicative set, it contains all its divisors. I put in parentheses multiplicatively closed for the following reason. Many authors apply saturated as a descriptor to an already assumed multiplicatively closed set. There's no reason that you have to do this. When I say a saturated set, I want to assume it's multiplicatively closed. I'll make it clear if I want it to be both, right? But you can have a set that's not multiplicatively closed, but it is saturated. Here is a quick question for you. If you have a ring with identity and you have a saturated set, what always has to be contained in the saturated set? Yes.
The identity, like one.
That's right, because the identity, in fact, more generally, any unit divides everything. So
Yeah.
a saturated set would have to contain all the units.
Mhm. You said how it works.
So, let me give you an example. Yeah, I and R, and by the way, you can assume now that rings are commutative with identity unless I tell you otherwise, is an ideal, then I complement, that is, everything in the ring that's not I is always saturated. But in prime, if and only if, oh, is, I'm sorry, multiple closed. If and only if I am prime. So if you look at the complement of an ideal, this is always a saturated set. But it's only multiplicatively closed, the ideal is prime. The units of R is multiplicatively closed and saturated. Anything that divides a unit must be a unit as well. Okay, so let me give you a definition. You see this, the theme of what's in this definition come up in commutative algebra quite often. The notion of maximality with respect to properties is an important one. Definition. We say that an ideal is maximal with respect to some property. Okay. Again, I'll talk about being very with identity, which you did for them. What do I mean by property? It's an integral domain. It's a polynomial ring. It's Noetherian. It's finite ring. So any property, right? So suppose that you have some property, some statement about this property here. So it could be a property of the ring or an ideal. I guess I could generally assume that the ideal could be a ring becomes it all. So the root might be finite, or the ideal might be finite. Generated, there's a lot of things. We say I is maximal with respect to P if I satisfies P, that it conforms to whatever the property of P is. And for all ideals, J and R such that J strictly contains I, then J does not satisfy. So what it means for an ideal to be, so you've got some property that an ideal might have, say that I is maximal with respect to this property, if it has the property, and any ideal that strictly contains it no longer has that property. You looked at an example of this in the homework where we had an ideal that was maximal with respect to intersecting some multiplicative subset. Let me give you a specific, this is the theorem that I said that you could use in the homework for this week. You just quote it, and I'm going to show you why it's true now. Or I'm not going to show you this one, I'm going to show you that. The next one is the piece that I want. Here. I'm not going to prove this one, this is homework exercise. Let R a uniform one and I deal this a multiplicative set. If I is maximal with respect to the exclusion of S, this means exclusion of S means that there's no overlap between I and S, and J intersect S is not in. Yeah, J is strictly contains I. Then I prime. I left this as a homework exercise because the problem is not super difficult, but I think it requires you to think along lines that are important. So if you have an ideal that's maximal with respect to the exclusion of any multiplicatively closed set, then this ideal is always prime. Now, can anybody tell me, I think this begs an obvious question. So here's what this theorem says. Suppose I find an ideal and it is maximal with respect to the exclusion of some multiplicative set. In this ideal, what is an obvious question, I think, that this theorem begs me to answer? So we've got a fancy little trick here, right? We know that if I have a multiplicative set and there's an ideal that's maximal with respect to missing this multiplicative set, it has to be prime. How do we know there's such an ideal? To me, that's the question. So suppose I walk up to you on the street, I give you a multiplicatively closed set. Can you find an ideal that is maximal with respect to missing this set? Because that ideal will have to be prime, right? The answer to this question is yes, which is really kind of cool. And it depends, once again, on the actual choice, Zorn's limit theorem. 947. If I intersect S is empty, here, I and R is an ideal. And S is a multiple closed subset. Then there's an ideal. There's this ideal. J containing I such that J is maximum with respect to excluding S. J intersect S. And it's maximal with respect to this property, any bigger ideal, any ideal that contains J's. Notice that by the previous result, oh, by the way, there it exists. In most cases that you encounter in nature, the J, the one that's maximal, is not unique. In fact, if you start with an ideal that misses multiplicative set, there may be many ideals that are maximal with respect to exclusions, but of course they won't be comparable. If there's multiple ones of them. Note the J from 947 must be prime. By this. Let's prove this. This once again is a Zorn's limit strategy. Suppose I intersect S into let's do my notation here. So yeah, there. So let's let gamma be the collection of all ideals of R. Right. Let gamma be the collection of all ideals of R that contain I and miss S. Of course, again, I don't want to sit up here wasting your time proving theorems about the empty set. So I need to make sure the gamma is not empty. Give me something that's in gamma. I.
Also, with your ideal.
Yeah, sure, that'll work too. Well, no, zero ideal may not work if you got this condition here. Right, because I notice that gamma is not the empty set as I as gamma. Notice that gamma is a partially ordered set. Under So take two of these ideals, A and B, then, we say that A is less than or equal to B if A is contained in B. But two ideals in gamma may not be comparable, but it is a partially ordered set under inclusion. To apply Zorn, what we need to do is need to show that any chain has no count. So here I'm gonna call my chain. This collection of ideals. Be a chain. So remember what that means is if I alpha and I beta are in this chain, then one of them contains the other. That's what it means to be a chain. It means that that's a bushel of apples. There aren't any oranges there. I can compare everything. Now, Zorn's lemma. I need to show that every chain, this collection of ideas, has an upper bound. Given the theme of the last time that we visited Brother Zorn, any ideas on what an upper bound might be?
Protestant
And that's products of ideals tend to be small.
of the,
You want the union, which remember is not usually an ideal, but because this is a chain, it is. U, the union, alpha. Certainly, I alpha, is contained in union for all alpha. So this would be an upper bound of the chain. So U is an upper bound. Need to show U is actually an element of gamma, right? Because the upper bound of the chain has to lie in the set. Right? Well, what does U have to satisfy to be in the chain? And I'll go kind of quickly on this because this is very similar to what we did before. Yes. Oh, well, talk stress. U and R is proper. Because one is not in U. If it was in U, and if one was in U, it would have to be one of these I alphas. These are also going to be proper. So I've got that with it. What else do I need from them? I need it to be an ideal. Well, so I'll just skim this one. If X, Y are in U, then X is in I alpha, Y is in I beta, and without loss of generality, I alpha is contained in I beta. Because one of these two has to contain together. Yes.
Why must you an ideal again?
That's what we're showing.
Oh,
Right. If X and Y are in U, then X lives in one of the I alphas, Y lives in some I beta. And so since I alpha without loss of generality is contained in I beta, that means that both X and Y are now I beta. So it's a subgroup and it's vacuum. So it's an ideal. We need it to contain I. But for all alpha, I is contained in I alpha, which is contained in unit. So I've got that. And finally, I need that intersection, the finally, suppose X is in U intersect S. Then X is in I alpha, with some alpha. X is in S. Therefore, X is in I alpha intersect S, which is the empty set. That's a combination. So U is in gamma. Zorn's lemma applies. And so there exists an ideal maximal with respect to exclusion variance. So that is a super duper theorem. And couple that with 946, and we've really got something to brag about, because any such ideal is prime. So let me put together a couple of really nice corollaries that are useful. Corollary 948. Let I be an ideal. So this is quite obvious to you all, but I think it's worth reporting. The ideal. And S, the multiplicative set. If I intersect S is empty, then there exists a prime ideal P containing I such that P intersect S. So I often say for this one, we can expand I to a prime ideal that is maximal with respect to exclusion of S. The exclusion of S, right? You can sprinkle a little fertilizer on this and grow this up to a prime ideal P that is maximal with respect to exclusion of S. So your original ideal that misses S is like the original seed, and you can grow that to a prime ideal that misses S. And second corollary. If R is a commutative ring with 1 and I is an ideal, then I is contained in the maximal. I is proper ideal. Then I and where M is some maximal ideal. This is a theorem we had earlier, but I wanted to recapture this for you from this notion of expanding ideals, because this is a slicker way to do it. Proof. So you all remember the theorem we had before, any commutative ring of identity has maximal ideal, and we started with any ideal is contained in maximal ideal. Here's the proof using what we know now. suppose I and R and property. Somebody tell me a multiplicative set that I has to miss for sure. It can't intersect with.
Well, it cannot contain the identity one.
Okay, so here's my set. Right? Notice I intersect S is empty. So there exists a prime idea. P, such that I is contained in P and P intersect S is empty. And P is maximal. With respect to property. One is not in P. So P is a maximal ideal. So P is an honest to goodness maximal ideal because it's maximal with respect to the property. The one is not in there, right? And any ideal that is maximal with respect to one that's not in there has to be a maximal ideal. Okay, any questions on it? All right, I probably plug the math club today because it looks like it's gonna be a really interesting topic. I hope y'all.